Hello, welcome back. This is a video solution for problem 9A from my spring 2020 final exam. Now you might be saying, wait a minute, didn't you have proof of that already? Wasn't that like yesterday's video or something? And the answer is yes. One of our listeners or viewers asked for a different solution. So the question they asked is, in your solution, that is my solution, I use the ratio test because, hey, factorials are usually a good indicator that we should use the ratio test. They want to know, can you use the root test? The answer from a theoretical point of view is yes. From a practical point of view is, well, it's going to look a little more challenging, but actually the interesting externality of trying to use the root test is that we will actually see a way of proving it using the comparison test and the geometric series test. So the root test is probably just not the right way to go about it, but let me show you where we go when we try to use the root test. So if we try to use the root test, then we know we're going to have to look at a limit as n goes to infinity of an nth root of this. And the problem is we don't really have a good handle on that. I'll write it. So we have an nth root of n factorial squared over 2n factorial. I'm omitting the absolute values because everything is positive. Of course, I could break this up over the numerator and the denominator. But it's really not clear what I'm going to get. So I have some rules for using the root test. For example, as n goes to infinity, the nth root of n factorial is infinity. Of course, if I have n factorial squared, that's not going to make it any less infinity. And if I have 2n factorial, it's also going to go to infinity. So in a sense, you have to kind of know which is going to infinity faster. So here's what we're going to do. Instead of jumping into this limit, we're just going to play with the underlying sequence a little bit. So I have n factorial squared over 2n factorial. So of course n factorial squared, that means I'm doing n factorial times n factorial. And I'm going to break up this 2n factorial as well. So this means you multiply from 1 all the way up to 2n. But I want to break it up into two pieces. First, I'll multiply from 1 to n, which is actually another n factorial. And then I'll go the rest of the way from n plus 1, n plus 2, all the way up to 2n. And I do that because now I can cancel some n factorials. And so I'm left with n factorial, which in fact, instead of writing n factorial, let me write it down. I can write this as 1 times 2 times 3, etc., up to n over n plus 1, n plus 2, n plus 3, up to, well, n plus n, which is 2n. Okay, so I make a little observation now, which is that these sort of look like they line up. The biggest one I get is going to occur when I look at the end, n over 2n, right? So n over 2n is equal to 1 over 2. As I go back down this list, I'm actually going to be getting some things that are smaller. It may not be immediately obvious to you, but let's do a quick example so you see what's going on. So let's say we took n to be, I don't know, say 6. So I would have 1 times 2 times 3 times 4 times 5 times 6 over 7 times 8 times 9 times 10 times 11 times 12. So you can see 6 over 12 is a half. As I go down, 5 elevenths, 4 tenths, 3 ninths, 2 eighths, 1 seventh, these are getting smaller, these fractions. So this is a nice little property of numbers that you can prove that if I have, say, some ratio, m over n, and then I look at m minus 1 over n minus 1, that will be a smaller fraction, at least under the right circumstances for m and n. So So what's happening here? We know that each one of these pairs, right, up and down, is going to be less than or equal to 1/2, the biggest one we have up here. And so this product is going to be less than n copies of 1/2 multiplied together. So what we've just shown is that each term in the sequence is bounded by 1/2 to the n. And so now, if I take this limit of the nth root, has to be bounded by the limit, as n goes to infinity, of the nth root of 1/2 to the n. And now the n's cancel, and I just get 1/2. Okay, since this is less than 1, the root test tells us that the original series converges. Okay, so this implies convergence. All right, but there's really no need to use the root test, actually. Once we identify that the sequence terms are bounded by 1/2 to the n, then by the comparison test, and by the geometric series test, right, we know that this series, n factorial squared over 2n factorial, converges, since the geometric series, 1/2 to the n, converges. In fact, we know exactly what it converges to. All right, so it's okay, of course, to use the root test here, but in some sense, once you've figured out that the underlying sequence is bounded by 1/2 to the n, I don't know, maybe it feels like overkill whipping out the root test when you're really just saying, well, my series is bounded by some geometric series, so which converges. All right, well, I hope the viewer is satisfied with this answer. I think one of the beauties of this part of the subject is there are so many different ways of attacking these problems, only bounded, no pun intended, by your curiosity. All right, enjoy.